So it's nice to see you again. So this is my second topic for today. The title is the benefits of GAN in a motor drive, but actually we will introduce to you and discuss with you about the TI first industrial GAN IPM, the industrial intelligent power module, DRV7308, and we will highlight the advantage of the product over the conventional IPM. And but before that, we will quickly take a look about the MOSFET switch transition and also the gate driver switching features. And from there, you will see the the highlight of the advantage of the device. Okay. So first is the introduction. You see that nowadays more and more appliances and also other equipment in a house they have a requirement to be more efficient, to consume less power, and the product can go very broad, from the appliances, heating and ventilation, air conditioning, efficiency system, and also other home appliances product which has the motor drive inside. And the user will expect the end equipment to have high levels of power efficiency and the reliability, that is from the consumer, the user. But from the manufacturer, the maker, they the variable frequency drive VFD solution is used to improve the system efficiency if they have accurate and wide speed control. And actually VFD is the system that uses actually the inverter to control the motor speed at the high frequency pole width modulation switching. And okay, so before we move to the detail of the TI GaNs IPM, let's discuss a bit about the MOSFET switch transition here. So this is the simplified schematic symbol of the gate. We have VGS, VDS, and also the IDS, VGS, IDS, and VGS here. So basically, on the left-hand side, your left-hand side here is the MOSFET turn on timing, and on the right-hand side is the turn off. So basically, in general, the sequence of these two on and off status is in the reverse direction. Reverse order. Let's take a look at the MOSFET turn on. There are four. Actually five, but here I noted four only. There are five stage of the turning on status. At T0 here. T0 here is during T0 the MOSFET is off. Is in off stage. At the end of the T0 the VGS start to increase. And then yes, and when it reach the V threshold, VTH, which is the end of the T2, the current IDS start to increase, and the VDS start to decrease. No, I was wrong. At the VTH, the IDS start to increase, and the VDS stay at its initial value. So by the end of T2, when the VGS reach the V plateau value, the IDS reach its maximum value and the VDS start to decrease here. And T3, the VGS stay as the constant, and the VDS continue to drop to decrease to the zero value, and IDS stay at the maximum value. And after this T3, so the VDS continue to increase to its final value. The VDS reach approach close to the zero, and the IDS is still at the maximum. So you can see here in the state T3, T2 and T3, IDS, because IDS and VDS are different from zero. So at this two stage, the power loss, the switching power loss occurs, and because of the switch, this is the contribution of these two regions into the power overall system power loss is significant. So we all want to narrow down these two regions by switching switching faster, and this and similar to the turn off sequence, these two stage T3 and T2, the IDS and the VDS are different from zero, so the power loss occurs in this region. Okay, next is about some feature of the gate driver. So due to the nature of the application, we always usually see the power MOSFET in the half bridge or full bridge configuration, and due to this nature of the scheme of the configuration, there are the gate driver needs to have some feature that support the switching control of this configuration. The first feature I would like to mention is the propagation delay, which is the time measure between the point that the inputs go high until the output go follow the input signal go high as well. So this time we call it a propagation delay. And also one of the feature of the gate driver is the dead time. Dead time is the time interval at which in which both the output both the input of the signal is stay at low stage. The purpose of this dead time insertion is to prevent the cross conduct between the two high side and low side switch, which cause the short circuit and also the a lot of the power loss here. So, okay, this is another feature or some other features of the gate drivers. We can mention here is the interlock and also the CMTI DVDT immunity. So interlock is the feature of the device to make sure that when both input signal is high, the output must be low. Whenever the circuit detect that the both input is high, so it will pull the both output to the low stage. So this also prevent the situation that both high side and low side MOSFETs turn on at the same time to causing the short circuit. We call the shoot through. CMIT or the VDT immunity is this is the dv per dt is the measure, is the slope. It's kind of the slope. I mean the slope of the what to say? It's the speed of the speed of the change of the signal here. So this one is one of the important parameter for the switch, especially in the high voltage application, because at the high voltage, when you want to switch the device faster, then you need the voltage need to change quickly, so to achieve the high switching frequency. So this is also one of the important parameter. So just now all the parameters I mentioned here, they have the impact to the goal. Our main goal is to switch the power switch as fast as possible, and all the parameters just now I mentioned have the impact on the the speed of the switching frequency. So, and to address and because of this nature, like just now I mentioned, is the nature of the switch configuration. So this parameter are needed, to deal with the half-bridge or half-bridge switching, and because of that, it limits the switching frequency. So to address all the limitation, we introduced the GaN IPM DRV 7308. So this is the three-phase half-bridge GaN integrated together with all the smart feature for the application that require high switching frequency for in a motor drive application. You can see here is the basic spec. This is the supply voltage, the RDS on, and the big current. Currently, this device support up to 5 amps, and slew rate. This is the one important information. Output slew rate can be adjustable, like 5 volts per nanosecond, 5, 10, 20, 40 volts per nanosecond. So these are the key feature of the device. It offers low switching loss because it switches faster, so it can switch faster. So the region T3 and T2 just now I mentioned is narrower, and this is one key feature that this device offer. And because it can switch faster and it has a ultra low propagation delay and also dead time, and it offers the low distortion of the waveform. Because you see that, like just now you see because of the delay between the input and the output of the switching signal, so the output the output's waveform will be like distort. It's not like fully clean, and it's distort. It cannot be like the original step that we need. So with this GaN, because it has the propagation delay and also the dead time very low, so it's offer very low distortion. We also have the integrated amp for the current sense. We have the temperature sensor integrated also. Okay, so this slide showing you the reason why you can consider GaN in motor drive. So compared to other conventional power switch like MOSFET and IGBT, at the power range at output is power is maximum is at 250 volts here, and the comparison here for also for the 150 volts. You can see that this is the power loss for the of the MOSFET switch. This is the IGBT and this is the GaN. So in general, the GaN has the highest efficiency, so it can be like more than 50% reduction in power loss. And with the DRV7308 GaN, you can increase the efficiency like just now I mentioned. And also because of the high efficiency, you don't need the heatsink because it runs cool. It runs coolly, so you don't need the heatsink. Which in turn, because you don't need the heatsink, so you don't need to pay for the heatsink. That's reduce your cost, system cost, and you don't need the heatsink again. And also the size of the design is very smaller and lighter. And because it has the very low dead time and propagation delay, this parameter will lead to like your system will be will have less audible noise. It will be quieter, and also it's easier for us to do the EMI design. So this is why this IPM GaN IPM have to reduce the power loss, because it offers like zero reverse recovery. This is one of the pain point with the MOSFET, right? The MOSFET has the need to have the zero reverse recovery time. So that means you need to wait for the MOSFET to be recover before you move to the next switching cycle. So with the GaN, you don't need that. You don't need, because it offers like zero reverse recovery. And because the output capacitance is low, and this is compared to the IGBT, it doesn't have the turn-off tail current, so it also contribute to reducing the power loss. And the slew rate, just now you see that it has the adjustable slew rate. You can select the slew rate you want for your system. So it's provide you with the capability to optimize the slew rate for your specific system. And also, again, this is another factor is that the GaN has the low RDS(on), which lead to low conduction loss. Okay, so this slide discuss a bit further about how GaN increase the inverter efficiency. So, in terms of the power switch, there are two types of the loss, right? Power loss, right? The conduction loss and also the switching loss. So the conduction loss could be considered as the similar to the across the three power switch types here. But for the switching loss, the GaN offer more benefit compared to MOSFET and IGBT. So like just now I mentioned, GaN offers zero reverse recovery. So you don't need to, like for MOSFET, you need, because of the body diode of the MOSFET, you need to wait for a while until you change to the next switching cycle. And this requirement will limit the DI per dt and dVdt and cause the voltage phase node voltage ringing. And for the IGBT, you don't need, you need to add it anti-parallel diode to have the QR. So and next one is because the GaN can be switched fast. So and also the voltage and current can be the switch voltage and current can be controlled. So the DI, DT, and DVT, you can control this to minimize the overlap. And okay, so again, also offer lower capacitance to compared to these two conventional power switch. So this is this table showing the comparison between the output power between the IGBT, the available IGBT IPM at the application at the power output power level at 250 watts. So you see that there's a gap between the efficiency here. The GaN DRV7308 has higher efficiency. Okay, so this is the information about the heat sink elimination. Just now I mentioned that you don't need to add the heat sink to the design. So that means that you can save some money, right? So here this is the actual design for the 250 watts motor drive with the IPM DRV7308. So this is the reference design. You can find the information from TI.com. Yeah. So this is you can see that the maximum temperature is only like 66 degrees Celsius. Okay. So how the GaN IPM, TI GaN IPM enable lower motor cost. So the lower motor losses include high speed and low inductance motor needs high PWM frequency to reduce the current ripple. Why high current ripple create unwanted torque, ripple, and high Cooper and core loss, and also it creates inaccurate current sense result. So here, just now I mentioned about the switching frequency of the power switch, right? So for the MOSFET or IGBT, IPM, so normally they switch at 6 kHz to 16 kHz, but for this IPM DRV7308, you can switch faster at higher frequency. So let's talk a bit about the current sense. Okay, so this is the waveform of how we sense the current, right? So we will sample the current at the middle of the PWM waveform, but because of the distortion of the impact of the propagation delay, the signal the ID slide is like this. It's not nice waveform, right? Square waveform. So the actual midpoint will be here, but when we sampling it's here. So there is delta I. The errors in the value that we sense for the current. So that is the impact of the propagation delay. And for the DRV7308, the dead time and propagation is very low, at below 200 nanosecond. Okay, so let's talk a bit about the audible noise. So in our appliances, motor control system, like the fan, cooling fan in your family, or maybe the air conditioner, and also or maybe the fridge, right? One of the requirements that we need them to run smoothly, quietly. So, but sometimes, but there is a noise. So where does the noise come from? So the noise come from. So in motor drive system, the main source of audible noise, the torque ripple of the current distortion. So just now we mentioned, we talked about the propagation delay and also the dead time can create the current distortion, right? So that distortion will create the audible noise, and that current distortion, how distort current is depends on the PWM frequency, the dead time, and current sense accuracy. So for this, all these feature, GaN has better performance in compared to the MOSFET and IGBT. So we can switch IPM again at higher frequency to reduce the current and torque ripple, which result in the audible noise out of the audible noise of the frequency. Okay, this is the solution side information. This is compared to reason between the two solution, TI GaN IPM and also the IGBT IPM. You can see that there much difference between the size of the two design at the same level of the output power. You don't need the head with the GaN. You don't need the heat sink, and also and because you don't need the heat sink, so the size and the weight of this design is the lighter and smaller. Okay, so some design consideration when using GaN in motor drive. We have like slew rate control integrated feature inside the chip, and these are the option of the slew rate setting you can select. And when selecting the slew rate, it's a trade-off between the motor winding insulation and switching loss optimization. And lower slew rate option of the DRV7308 cover range is offered by existing IGBT and also provide 99% efficiency. And also again, the zero reverse recovery of the GaN with lower parasitic and low slew rate control enable clean switching, voltage switching. And this is the benefit of the consideration when design with the conduct and the related emission. How many time left? Okay, I have 3 more minutes. I will be quick. Okay, so we do have like the reference design and all the design resource you can access from the comment. From there you can see how we recommend to do the layout to achieve the better EMI and to address the EMI and EMC concern. Beside the switching feature that the GaN DRV7308 offer, it also has some feature like integrated some in protect features. It has the overcurrent protection for each GaN inside the chip, and we do have the VDD and bootstrap under voltage lockout, over temperature protection, dead time, input dead time, and current limit protection using the integrated comparator for the all 3 phases inside. Okay, so to get started, you can visit the links that provided here to study more about the product and also the reference design and also the some white paper and technical article discuss discussing about the why and how this can benefit you in your motor drive. Okay, so I think that's all for the IPM again, FTI. I hope that you. Okay, so maybe you don't have the question now, or and maybe later you have question about this product, and you can just send me an email or approach Aziz, so we can we go back to you with the information. Yeah, thank you.